So in part 3 of this video, we are going to start talking about how heat loss is measured, and we're going to talk about the building envelope and how we evaluate the building envelope for heat loss. By building envelope, we mean the outside walls or any area where there's a difference between the conditioned space, that's the inside space, and the outdoor space. Now, very important as we go through here, we're going to start talking about BTUs. BTUs per hour is how heat is measured. A BTU is approximately the heat generated by burning a wooden kitchen match. That's one of those older wooden matches that you can barely find anymore. Okay, a BTU is a quantitative measurement. BTU per hour is a rate. Okay. So a BTU is the amount of heat required to raise or lower the temperature of 1 pound of water, that's about 1 pint of water, by 1 degree Fahrenheit. Now if you do it in an hour, that's 1 BTU per hour. So moving on, we're going to start talking about the building envelope analysis. This is an important part of a heat load. You have to understand how much heat is entering or leaving a building for both heating and cooling. So in order to calculate the rate of heat loss, 3 numbers must be known. You must know the total area of exposed surface of the plane, the U value of the plane construction, and the temperature difference from one side to the other of the plane construction. By plane construction, we could be talking wall, we could be talking ceiling, we could be talking floor. Anything that is a basic plane, okay, like one directional. Okay, so we have to know the U value, the area, and the delta T. So the building envelope, as I mentioned earlier, is the part of the building which separates the inside environment from the outside environment. Inside walls are not included in a building envelope unless there's a temperature difference across those walls. In other words, if you have an unheated or uncooled garage and you have an interior wall that's separating the rest of the house from the garage, that interior wall that's actually separating the cold or hot environment from the conditioned space, that becomes part of your building envelope. Now, ASHRAE defines the building envelope as outer elements of a building, including walls, windows, doors, roofs, and floor, including those in contact with the earth. In other words, in a slab house or in a basement, the concrete slab that separates the basement or first floor from the dirt, that is part of your building envelope because there is a temperature difference across it. Now, buildings also have a thermal envelope. Okay, the ASHRAE definition of a thermal envelope: elements of a building which enclose spaces and which control or regulate heat and mass transfer, air, water vapor, and entrained moisture between the interior spaces of insulated floors, walls, windows, and ceiling generally comprise the thermal envelope. So let's talk about what different parts of the envelope. We have the skin, we have the shell, and we have the enclosure. That's the part of that's all of our building envelope. Building assembly is any part of the building enclosure that has boundary conditions at the interior and exterior of the building, such as a wall assembly, or window assembly, or roof assembly. A building component is any element or material within a building assembly. If we take a look at a wall or this window, you will see that there's more than one component. You might have glass, you might have the window ledges, you might have the casing which the window glass sits in, and then you have the brick around it. That's all part of those are all components of the building assembly. In this picture here, you have the insulation, you have the joists or the studs, you have the outer particle board, and then outside of that you might end up with having sheetrock or some additional material on top of it. Each of those is a building component. They will all have differences in heat loss and heat gain. The building enclosure is very important because, as was quoted from Mr. Anus, if your building enclosure doesn't work, your HVAC system may not work as designed, even after fine-tuning it until you're blue in the face. You cannot go through life as a technician or as an HVAC designer without understanding the building envelopes. Because if it doesn't hold heat in the building on cold days, and if it doesn't prevent heat and moisture from coming into the building on hot days, there's absolutely no way the building envelope will work. So the functions of a building envelope, first of all, is to control heat flow. Then we control airflow. Then we control water vapor flow. We control rain penetration. And we control light. We control solar and other radiation. We want to control noise. We definitely want to control fire. We want to provide the building with strength and rigidity. The building envelope has to be durable. It has to stand up to weather. And it has to be aesthetically pleasing. Okay, are there any other functions? Perhaps safety, security. Now, all building envelopes have different versions of mass, okay? Two structures of identical sizes, but different materials, such as wood frame and concrete block, can react quite differently to temperature variations. Okay, wood frame is going to pass heat and cold a lot easier through it than concrete block. Different sizes of concrete block make a difference as well. Coloring of wood or other outside building components make a big difference. The lighter frame building will warm up much faster than the heavy block building and will require less energy input in the process. However, the massive structure, which is the concrete block, will remain warmer after the furnace shuts off. The same effects are true during cooling season. In fact, we'll find out that this storage effect is even more evidence in the calculation of cooling loads. So we're now going to talk a little bit about U value, okay? The U value, remember, is the measurement of the ability of a building component to pass heat through it. Okay, it's a rate of heat transmission or thermal transmission through the material. The greater the thermal conductivity of the material, the faster heat passes through it when the delta T, or the temperature difference, is maintained across it. The lower the U value, the less heat is transmitted. Okay, that's a good thing. So the lower the U value, the better the insulation material is. The heat transfer per time period and per degree of temperature difference is also a definition of U factor. The U factor multiplied by the interior-exterior temperature difference and by the projected fenestration product area yields the total heat transfer through the product due to conduction, convection, and long-wave infrared radiation. The rate at which a window, door, or skylight conducts non-solar heat is also known as a U value. It's usually expressed in units BTU hour per square foot per degrees temperature difference. For windows or skylights and glass doors, the U factor may refer to just the glass and glazing alone. Okay? But National Fenestration Rating Council U factor ratings include the entire window, including frame and spacer material. The lower the U factor, the more energy efficient the skylight, or window, or door. Okay, lower U values indicate lower heat transfers. So if you take a look at this table and you want to find out which one has the highest insulating value, You want to find the lowest U value, which would be the insulating glass triple with a 1/4 inch airspace, because it has the 0.37, which is actually the lowest U value. But that means it's the highest insulating value. Lower U values indicate lower heat loss. So as I said, the 0.37 is your lowest one. Okay, a measure of heat transfer, thermal transmission. The greater the thermal conductivity of a material, the faster heat passes through it. R value is also used. If you go into Home Depot or Lowe's, you'll find that R value is listed on most of the insulating products. R value, it's simple. It's an inverse of a U value. So to find the R value of any product, just take 1 and divide it by the U value. Okay. So when we take a look at this insulating material, okay, we find which is the best insulating, okay, you find the lowest U value, which in this case happens to be blown fiberglass with the 0.185. Now, if you find the R values, which is the 1 divided by the U value, you'll find the blown fiberglass is 5.41 and is the actual highest R value. So again, it's an inverse relationship. The lowest U value is going to equal the highest R value. Now, higher R value numbers indicate greater insulating material. Okay. So some samples of standard R values. Okay, we want to find out which is the highest insulating value. So take a look and find that the foam in place urethane has an R value of between 5.6 to 6.3. It's going to be the highest R value. R value increases directly proportionally to the thickness, which is sometimes known as L, of the material. R values for different materials in a structure can be added directly. In other words, if I have fiberglass insulation covered by sheetrock, protected outside by particle board, and then some sort of architectural material for appearance on the outside, I can add each of those R values and I can use the total. A material rated at R11 is added to a wall rated at R3. The wall dimensions are 8 feet high by 20 foot wide. The inside and outside surface temperatures are 70 and 5 degrees respectively. Find the rate of heat transfer across the wall. Okay. Now, first you want to determine the total R value by adding the two given values. So we know our RT, which is our total, equals 11 plus 3, which is 14. Again, if we take a look at the previous slide, we have R11 and R3. So that's R14 total. Now, find the U factor. So U, if you remember, is 1 divided by R. So 1 divided by 14 is 0.071. Finally, you want to substitute the values into the conduction heat transfer equation, which is Q equals U times A times delta T. So 0.071 times 8 times 20, because that's our wall dimensions, times 70 minus 5. Do all the math within the parentheses first. So you come up to 0.071 times 160 times 65, and now multiply it straight across. Our heat transfer for that wall is 738 BTUs per hour. R values are most often used to compare thermal insulating products. Okay, it's a quantity resistance to heat flow. Okay, it's used to calculate heating and cooling loads. It's very important you find the correct R values. R value can be measured for specific conditions. They can be determined from physical property or system measurements. R values of materials most often are found in ASHRAE's Handbook of Fundamentals or in the product manufacturer information. Don't just guess at it. Look up the R values. So if you have a wall, okay, to find the total R value, you add up all the R values of the wall. So in this case, we have a 1/2 inch exterior siding with a value of R1. We have 1/2 inch plywood with R1. We have a 5.5 inch of fiberglass R19, and we have 1/2 inch sheetrock with R1. So what you do is you take and add all of these R values, 1, 2, 3, and 19. So we have an R22. Okay, then we take the reciprocal of that. So to find our U value, we have 1/22, which is 0.045. Gives us our U value. Now the FTC, Federal Trade Commission regulation, deals with home insulation labels and fact sheets and other promotional material. The purpose of the R value disclosure requirement for advertising is to prevent customers from being misled by certain claims on which have a bearing on insulating value. You don't want everyone just to be able to say, my product is better. Consumers must receive R values prior to sale either by a label on the insulation package or on a fact sheet. You can list a range of R values per inch. If you do, you must say exactly how much the R value drops per inch with greater thickness. You also have to add the statement, the R value per inch of this insulation varies with thickness. The thicker the insulation, the lower the R value per inch. Okay, so that is our basics of measurement of insulation, R values and U values, and also an introduction to the heat transfer formula, which is the Q times the U value times the area times the delta T, which is the temperature drop. In our next video, we're going to be starting to look at more of what affects heat transfer. We're going to talk about insulation and different things that affect the total R value.